Hello guys, welcome back to the TikTok frequently asked playlist. Today let's all verify pre-order serialization of a binary tree. Uh, so, so serialization basically means that given a binary tree, we want to represent that in some sort of a compact format, like for example a string format. Um and the process of deserialization basically means that we are given an input in a string format and we need to construct the tree back, right? So a node is typically represented as a node object with three attributes, like the value attribute and then the left and child attributes, right? So in this question, we are using a pre-order traversal. So just to recap, a pre-order traversal is where you process the current node first and then proceed to the left part of the subtree and then finally to the right part of the subtree, right? Uh, if if you are not very well aware with this sort of traversal or other traversals, I would strongly recommend you to read about these things first. So basically in this question, we are given an input string like this, like a serialized version of a binary tree like this, where hash represents a null node. So we basically just need to check the validity of this serialization. That is, we need to return true if this indeed is a valid pre-order traversal of any binary tree, right? And if it's not, we need to return false. So it is guaranteed that each value is either a digit or a hash, and we're also given that the format is always correct. Like we're not going to get inputs where we have like consecutive commas and stuff like that. And another important note is that it says that you're not allowed to reconstruct the tree, which basically means that we are not allowed to deserialize the tree. Like given this format, we are not allowed to actually construct an entire node, like with a node object and then populate the left and child attributes. So we're not allowed to do that. So we need to basically figure out a smart way to check the validity of this tree just from the string format, right? So let's see how to do this. So we have the same example here. So let's first try to do a pre-order traversal just to understand how the string is actually populated. So, so we start with the root and then we immediately process the node. That is, we print out the, the node value and then we go to the left part of the subtree and then we immediately print out 3. Then again we go to the left part of the subtree, we print out 4. So now we are at a leaf and then we try to go to the left but we see a null node. So we print out hash. As the question says, we represent null nodes with hash. Then finally we try to go right. It's again a null node. We print out another hash. So the left part is done. So now we proceed to the right part of 3. So we see a 1. We print out 1. Try to go left. It's a null node. So we're going to print out hash. Then again it's a null node. We print out hash. So now we're done with both the left and the right part of this subtree. So this subtree is done and then finally we go to the right section of 9. So we see a 2, print out 2 and then we try to go left first but we see a null node. So we print out hash and then we try to go right, we see 8 and then now we try to go left again. It's a null node, we print out hash. It's a null node again and we print out hash, right? So this is basically the pre-order traversal of this binary tree. So in this question, this is the input that we are given, right? So we are given an input like this. So we need to check in a smart way if this indeed can actually represent a valid binary tree, right? So let's see how to do that. So the key idea of this problem is the fact that the length of the string is a direct indication regarding the validity of this tree. So let's see how. So let's say we start with a root node. When you see a node which is not null, this immediately means that I need to see 2 more nodes, right? So if you're crossing a string and you see a node that is not hash, it means that
I have to see two more nodes for it to be valid, right? And after processing a particular node, we need to just mark that, all right, we have actually seen this node, so let's reduce the number of nodes that we need to see, right? So all we need to do is just have like a running counter called, let's say, need to see, and this running counter starts with 1. I'll explain why later. And anytime we see a node that's not null, we're going to increase by 2, and after the processing a certain node, we're going to decrease it by 1, right? So what is a valid binary tree? It means that after processing this entire string, the it's valid only if NTS is 0, which means that uh, I have seen all the nodes that I need to see, and so it's valid. And another uh, a terminating case is that while processing this tree, if at any point NTS becomes less than 0, let's say it takes a negative value of -1, that means that you're saying I need to see -1 more nodes. This doesn't make sense, right? So we immediately return false, saying that it's not a valid tree. It can never be a valid tree. So let's just take one base case where we have like an edge case where we have a null tree. It basically means that it has no nodes. So what would be the string representation of it? It's just going to be hash, right? So that's the reason why we're actually starting NTS. We're starting NTS with 1 because we are allowing so before you actually start processing the tree, you're saying that I want to see at least one node right now. Okay, so if it's a null tree, you just start with hash. Okay, I've seen a hash. That means that I'm done seeing one node, and NTS becomes 0. So this is indeed a valid binary tree, right? So let's say we have an input which starts with hash and then has like 1 and 2. So this is definitely not a valid tree, right? Because once you have the root node is null node, a null node cannot have any more children, right? So we immediately need to return false, right? So let's see how to code this.
All right, let's first convert the string representation into a list representation, uh, just so that like iteration is easy. We don't want to be dealing with strings here, so that you can do with just a split method. You can just split on the comma and you're going to get a list. Now let's iterate over this list, uh, and before that let's initialize this variable called need to see that I was talking about and initialize it to 1, right? So this variable basically tells us that uh, how many more nodes that I need to see for this representation to be valid, right? So uh, so now we're iterating a list, and once we see a node, that means that okay, I have seen one node. So let's quickly mark that, saying that uh, mark that you have seen this node, right? And uh, at any point, if you notice that need to see becomes negative, that doesn't make sense, right? You can never say that I need to see -1 nodes more. That means that this representation can never be uh, a valid binary tree. So you can immediately return false. You don't even need to go through the remaining elements of the list, right? And then finally, when you see a non-null node, uh, that is if node is not equal to a hash, that means that uh, I need to see 2 more nodes, right? For it to be valid. So that's about it. That's pretty much about the entire code. And finally, we just need to check the last value of need to see. So it's valid only if need to see is 0. In that case, you return true, and for all other cases, you return false, right? So let's just check if it works. Yes, it works. Let's run it with the other test cases as well. It works as well. And let's submit. All right. Uh, yeah. So this logic might not be very may not strike you immediately, but you see how it's a very neat trick uh, to directly check the validity of a tree without even constructing it. uh, and and yeah, it's pretty efficient as well. Like you just iterate over the list once, so the time complexity is n and the space complexity is 1. Like you pretty much don't use any extra information, right? All right. Thank you for watching.